Today's lesson is day 3 of chapter 3 curve fitting, and we are going to dive right in with the example we're going to use to illustrate what's new for today. So it says, suppose that a population of 25 rabbits is introduced to a small island. As time goes on, the rabbit population increases. The table below gives the population data. So I already have this data put in the calculator in the interest of time. And the first thing it's asking us to do with this is to use an exponential regression, or use exponential regression to find an exponential model for the data. All right, well, I want to get a scatter plot first, and then I'll do that. So I'm going to go to stat plot, choose the first one, turn it on, scatter plot option, L1, L2, mark color, that looks good. I will build a window that makes sense in the context of this problem. We're going from 0 to 9, so I'll go like -2 to positive like 15. Scale if I say 2 probably works out pretty well. 25 to 82, so my y max to be about 100. -10 probably works well. Scale it by 10. Hit graph, and looks pretty solid. We can adjust that window later if we need to. All right, now getting the exponential of best fit. Stat, calc. Oh, you know actually what I want to do before I do this? Make sure my diagnostics are turned on. Second, catalog. Further down than I thought it would be. Diagnostics on. Okay, now do my curve of best fit. So we have stat, calc, exponential of best fit, L1, L2. I want to put this right into Y1. Calculate. Just for the sake of having a record of this, so our exponential is going to be in the form y is equal to a times b to the x, and we'll go 2 decimal places just for writing this down, 26.31 and 1.15. My correlation, my coefficient of determination is about 0.986. And my correlation is about 0.99, 3 decimal places. Okay, let's take a peek, make sure that's in Y1. Yes, it is. Hit graph. And that's what we get. So, seems reasonable. It's not a perfect fit, but it's certainly not like awful bad. I'd say that that's pretty reasonable based on what we know. All right, just sketching that onto here, we're not going to be doing that for today's classwork at this stage of the game, which is far too time-consuming. We will bypass the copying the graph over. Okay, number 3, use the model to estimate the population for T as 20, 30, and 50. Okay, the way that I'm going to do this here is I am going to go to my table set, put it on Ask Auto, go to my table, and then plug in those values. So, T is 20, 30, 50. 20, 30, and 50. All right, now we're talking about rabbits, so probably good to round to the nearest whole number. So we have 395, 1532, 2302. And that is the prediction based on the exponential model. So a couple questions from now, they're going to be asking us about a different model. I'm going to leave that table there to do the comparison with, for the end of that table. All right, now yesterday, we started off with an exponential equation, and we said, is there something better out there? And it turned out for the data from yesterday's problem that power was a better fit for the data than the exponential was. The new thing we're going to look at today, the fourth and final Chapter 3 curve fitting option, is logistic. So what I'm going to do here, quit out of that, stat calc, and then it's nice because they group together all our Chapter 3 stuff in one little area. You have natural log, exponential, power, and logistic. And let's put this equation directly into Y2 and calculate. Now, one thing that you'll notice most likely on your calculator is it's going to take your calculator a little bit longer in order to get the answer. The calculation is a little bit more intensive. So is the equation. When you do a logistic of best fit, it's going to have this format to it here. I'll copy this down here. So y is equal to c over 1 plus ae to the negative bx power. So, for our equation here of what the calculator says is the logistic of best fit, the A is about 4.37, the B is about 0.23 if we go 2 decimal places, and the C is about 130.67 if we just do a consistent 2 decimal places. Now you might notice that we didn't get an R and R squared. The R and R squared are a byproduct of a very specific algorithm that the calculator uses for some of its curve fitting. Okay, for the, what do we do? The exponential, the logarithmic, and the power, we got R and R squared values. For logistic, we're not going to get it. The algorithm that produces this logistics equation does not lend itself to an R and R squared. So when it comes to deciding which is going to be better, that exponential of best fit or logistic of best fit, we lose that R squared comparison in order to make. Let's take a look at the graphs here. So the blue curve is our exponential of best fit. And now the red curve, I think it's going to be red, that's coming in is the logistic. All right, it seems to fit a little bit better. Okay? Visually, it looks like it's a little bit more consistent with the overall shape of the data than exponential. Okay, what we're going to need here is some kind of context to decide which we want to choose. And what I'm going to do is hold off on that because there's some other like more mechanical things I want to do, and then we'll get into the whole context thing. All right, so we found the logistic model. That's this guy down here. Adding the graph to the logistic model in a scatter plot. We're not going to be copying it on the paper here. We're just going to work off our calculator screen. Use the logistic model to estimate the population for this. And what I'm going to do here is go back to the table, and those other values are already like still here. We're good. So to the nearest whole number, we got 125. We got 130, and we got 131. So pretty radically different predictions depending on which model we ultimately decide is best. So we'll leave that alone for now and go back to talking about which one's going to be best in context as soon as we wrap up the mechanical stuff. So add to this we did, which do you think would be better? This is kind of what we're going to be focusing on now for the remainder of the time. All right, the true effect of what's happening with a logistic curve, we're not seeing very well in this window right here. what I'm going to do is expand my window out to get a better macro view of what's happening here. All right, so I chose 15 for the X max because of the fact of it's a little bit bigger than that 9 value. Well, we have X values or T values going all the way up to 50 here. So let's say like 75. Let's go to 75 for that, and we'll scale it by 10. And then for a maximum, let's go up to say, like here, we had 395 as a predicted value, 1500. I don't think we want to go quite that big. Let's go up to say like 500. And we'll scale it by say like 50. And hit graph. And the logistic, again, is going to take a little bit longer to plot. Because it goes on, or it's a more complicated equation. Now, we're going to want to zoom back into this data in a little bit. It's all getting smushed in. I just wanted to show you the overall end behavior here. An exponential graph continues to grow forever up in this direction. What happens with a logistic graph is it grows initially like an exponential, and then it levels itself off. So let's do this. I'm going to zoom box this. Move as far over as I can. This corner. And enter. And then we'll just get this part right here. And then enter. And I think this will give us a pretty good visual of what we want to look at. So right here in the beginning, both curves seem to be kind of following along. And then we reach the point where the exponential keeps growing exponentially, and this one kind of levels off like this. So the red curve appears to fit that like little secondary curve of the data better than the blue one. The other thing I'm going to go to is the fact of they specifically said a small island. So we're talking about a small island. There's a limited number of resources on a small island. You can't have a rabbit population of, say, 23,000 on a little tiny island. There reaches the point where there simply isn't enough food or little green meadows for our buddies to hop in if it's a small island. So there's a limiting factor here to how much this population can grow. And that's what a logistic curve takes into an account. A logistic curve takes into an account of the fact of you have a limited number of resources. Like a grimmer version of this same question would be the planet Earth. Eventually, the planet Earth is going to reach the point where there are more humans than there are resources in order to support us. So at some point in time, the planet is going to reach a maximum population, that upper bound here, where it's not going to grow anymore. That there simply can be only a certain number of people on the planet Earth. Just like on this island, there's only a certain number of rabbits that are going to be able to survive. So that is the difference, or one of the key differences between exponential growth and logistic growth. Exponential growth continues that pattern on forever. Logistic growth takes into an account some external set of circumstances that are going to limit the actual ultimate population being described by this particular, or by the particular problem in question. All right, so going back to this, the logistic model is going to be better, and we can do a combination of that curve appears to fit the data a little bit better, with it going back and bending the other way, in combination with the fact of we do have a small island, which would indicate a limited number of resources, a limited amount of resources. Okay. Now on to some features that are important in dealing with the logistic curve. And these notes are included on the assignment you guys are going to be working on as part of tonight's homework. So, this is the blank form of a logistic equation right here. Same form that the calculator uses. The domain of this function is all real numbers. Now, the domain in the context of a word problem may not necessarily be all real numbers, but in terms of the actual sketching of this graph, there are no restrictions on x. It goes on forever to the left and right. Okay, the range goes from 0 to c, uninclusive here. Okay, now the range of 0 we're not really getting in this particular picture. What I'm going to do is let's change the window to from like negative 50 to positive 50 in the x and y direction. And we don't really want the blue curve. I should have turned that off. Okay, the graph is never going to go below the x-axis. It turns out that the x-axis is the horizontal asymptote for this graph. And the graph is never going to go above the other horizontal asymptote that it has, which corresponds to that C up top. So if we were to trace this here, oops, not on the curve. If we were to trace this here, and we look at these y values, we see that the y values are never going to get above that 130.67 number. That's the top limiting factor. So we're going to have two horizontal asymptotes. The lower one is going to be the x-axis, or y is equal to 0. The upper one is going to be at y is equal to c, which means that's the upper bound of the range, which is going to be that top number right there. So in context, the horizontal asymptote typically represents the maximum sustainable population, which is also referred to as the limit to growth. So based on this particular model, this island is never going to be able to sustain more than, you could justify 130 as in the rounding down. The island is not sustainable for 131, or you could, I just realized you're not seeing what I'm pointing to. Apologize. Okay, so that C value for the rabbit problem is 130.67. So that's telling us that either 130 or 131, depending on how you want to justify the rounding, is the maximum sustainable population on this particular island. All right, another thing that's relatively important in the study of logistic curves is the maximum point of growth. So what's happening here is you have a curve that has the x-axis is a lower asymptote, goes up like this, and then has an upper asymptote here at y is equal to c. And you reach a value in here where it starts to turn the other way. That this is where you reach the point of maximum growth. Okay, that is known as the maximum growth point. Generically speaking, it's a point of inflection. Points of inflection we've addressed a couple times in the class. This neighborhood here, we're concave up. This neighborhood here, we're concave down. Well, somewhere between concave up and concave down is a point of inflection. That's where it changes concavity. Now, the actual why this works is based on calculus. The why where that comes from, we don't really care. The fact of the matter is that given these values, you're expected to be able to figure that out. So the point of inflection will be the x-coordinate, the natural log of a over b, the y-coordinate of c over 2. All right, so today's lesson overall, kind of two worlds we're talking about here. Number one, in purely just a curve-fitting world, the fourth option that we're going to be considering in our group of Chapter 3 curve fitting is a logistic. Visually speaking, what happens with logistic is it starts off as looking like it's exponential, You reach a point of maximum growth, and then the curve starts to bend the other way. Okay, so from a pure graphing point of view, that kind of wraps up the curve fitting. In terms of a topic in and of itself, these are the algebraic features of a logistic growth curve. Now, tonight for homework, you're going to have a worksheet, which is going to be a blend of the two skills. You're going to deal with some questions that you're already going to be given, logistics curve question, and what you're going to have to do is identify some features of the graph. Some of them will be generic, and some of them will be in the context of what's happening in the problem. You'll also have a couple problems where you are going to have to get the data in your calculator first, get a logistic equation to match that data, and then answer some questions based on your equation. And then the last couple, these guys are pretty challenging. I'd like you to try them on your own. Probably what we'll end up doing is I will do them for you in class tomorrow is my best guess, or the next time that we end up meeting with this particular topic. Okay, I think that wraps up today's lesson.